In this lesson, we are going to look at the mathematics of the rotating coil. Now, the good news, the really good news, is that the mathematics of the rotating coil is much easier than that conceptual approach of thinking about whether the current is moving towards the point P, away from the point P as the coil, rotates through the 360 degrees. And you definitely want to use the mathematical approach to problem solve. You don't want to have to sit there and conceptually go through an entire rotation or even part of a rotation. So let's see what we're looking at. Well, the perspective is the same in terms of the B field coming at us. So let's get a B field in here. It's coming at us, so let's get us in here real quick. So this part is the same, the perspective. We're looking at a side view, so we start facing the full face of the coil, so the n hat vector is here, is here coming at us. If we were going to put a point P in, we're not, but if we were going to put the point P into the problem, the point P would be up here, and it would be rotating away from us. So let's take a look at the flux through the coil based on the mathematical equation B dot n hat A. We don't have to integrate A because A isn't changing in the problem, it's rotating. And look at what we get right away. Right away, we get BA cosine theta. Namely, we get cosine theta, which oscillates between 0 and 360 degrees. So that is what the mathematics is going to give us to allow us to analyze the rotation of the coil. The angle theta in a dot product is always the angle between the two vectors, in this case the B and the n hat, drawn from a common origin. So that's why I have the theta highlighted here, and that's what is changing. So if we're rotating the coil at a constant rate, meaning we're going to rotate it at a constant omega, so omega is the rotation of the coil, the radians per second. So theta equals omega t plus phi. Phi is the starting angle, so at t equals 0, right? We get 0, and we're going to use our unit circle here for an n hat rotation through 360 degrees as our conceptual visualization now. So the n hat vector is going to be rotating through the 360 degrees. The B field remains fixed, so the angle represents the angle between the B field and the n hat vector. Remember, the B field is staying at 0 degrees, so it's held fixed at 0 degrees. So the B field is here at 0 degrees. Whoops. And as the n hat rotates, we get the angle between the B vector and the n hat vector. And that's really it. We're done. So we are just going to take the derivative of d theta dt. The derivative of cosine is opposite sine, so we get our positive out front. The derivative of cosine is opposite sine theta d theta, so when we take the derivative of the inside, we get the omega. And this would be our answer for a single coil. If we have many coils, then we simply multiply by n, and look at what we get. We get that the induced voltage is omega w NBA sine omega t plus phi, and the easy way to remember induced voltage in a rotating coil is WNBA, women's basketball, WNBA sine omega t plus phi. There you go. And you simply plot out a sine function. So we have the sine function. We have, look, the maximum voltage is WNBA. And we have our oscillation from 0 to 360 degrees. So we definitely are going to utilize the mathematics rather than that conceptual rotation. So when you draw in your sine here, let me give you a little trick for drawing nice sine functions. Don't try to draw the function with a straight line. Make little dashed lines. So believe it or not, your hand is going to give you a much nicer, much more pleasant looking sine function if you kind of make a dashed one. Try it. Trust me, it'll look nicer. All right, so there's the basic mathematics, and let's apply this to a problem with actual numbers. So if we have a rotating coil, we're told it's a 50-turn coil, so there's our capital N. 50-turn coil, we're told that it's a 10 centimeter by 20 centimeter coil, so there's our area. And we're told the external B field is 0.5. We are told that it is rotating at 60 revolutions per second. So here we have to be a little careful. 60 revolutions per second is not omega, right? It is frequency, and omega, if you remember from mechanics, is 2 pi f. So instead of having theta equals omega t, we're going to have theta equals 2 pi f. And by the way, if they don't give us a starting angle that's not 0, use 0 for your phase angle, right? Your phase shift. So if they don't tell us to choose something other than starting it with the full plane lined up with the B field, then start it there. So the mathematics I have is identical to what we just had on the last page. We have our dot product. Check. We put it from omega t into 2 pi f. Check. We take the derivative. WBA, so it becomes positive. WBA sine theta becomes WNBA sine theta. And we plug in the values we were given at the top of the page to get our actual voltage with a maximum voltage of 188.5. So we can see how this rotating coil generates an AC alternating current voltage, and that those rotating coils, those N coils, are going to become the N coils of turbines that rotate in uniform fields that generate the AC electricity that is sent off to all of our homes, and we'll talk more about that as well in class.